Hi, and welcome to AP Chemistry Review. It's me, Dr. V, and it's my favorite time of the year. This is the time of year when we start going through free response questions from past AP exams. In this webcast, we're looking at free response question number 3 from the 2021 exam. If you're familiar with the AP Chemistry exam, and at this point you probably are, the first 3 free response questions are long free response questions, and they're scored out of 10 points, and this one is too. Before we go any further, grab your calculator, get your periodic table, have your AP Chem formula sheet handy. Let me introduce each part of the problem, and then pause the webcast, try to work through it on your own, and then listen to my explanation. Your goal here is to get better as a chemistry student, and trying it on your own is going to be more effective than just listening to me talk. And then you can keep track of your own work as you go and score it. Did you earn the point or didn't you? And what do you need to do to enhance your answer to make it more complete? And that's really what I want you to be thinking about as we go through this. All right, let's jump right into the problem. A student is given the task of determining the molar concentration of a copper 2 sulfate solution using 2 different procedures, precipitation and spectrophotometry. For the precipitation experiment, the student adds 20.0 milliliters of 0.200 molar barium nitrate to 50 milliliters of the copper 2 sulfate solution. The reaction goes to completion, and a white precipitate forms. The student filters the precipitate and dries it overnight. The data are given in the following table. So we've got this really long setup. We haven't even gotten to the first part of the problem yet. So finally comes part A. Write a balanced net ionic equation for the precipitation reaction. So I've hidden all the things that aren't part of writing this equation. We've got barium nitrate reacting with copper 2 sulfate. And we know we're going to form a precipitate. It's a precipitation reaction. These are double displacement reactions. So the cations switch partners. So we can think about writing a complete molecular equation and just writing a regular balanced equation like you might have written in your first year chemistry class. So we have barium nitrate and copper 2 sulfate. We know the cations are going to switch partners. Let's think about ion charges before we write those formulas. You need to pay attention to your formula writing rules here. So the barium's got a +2 charge. It's with nitrate, which has a -1 charge. The copper ions have a +2 charge, and they're with sulfate ions, which have a -2 charge. So the barium ions are going to end up with the sulfate, and the copper 2 ions are going to end up with the nitrates. And we need to make sure we put them together so that we end up with neutral compounds. So we're going to make barium sulfate and copper 2 nitrate. I did go ahead and put these states of matter in. How did I know that that's what was going to happen? Well, there are solubility rules. And one of the important rules that AP Chem students need to know is that all the common nitrates are soluble. And that means the product copper 2 nitrate, I'm going to mark it as being aqueous. It's soluble in solution. And that means barium sulfate must be the precipitate. And that's how I figured that out. But this isn't what I need for my answer here. I need a net ionic equation, and right now what I have is a complete molecular equation. So one way to get to what I need is to write a complete ionic equation. Take all my aqueous ionic compounds, and they dissociate into ions, and write them that way. And then, of course, the precipitate would stay together. So the barium nitrate is going to make barium ions and nitrate ions. The copper 2 sulfate is going to make copper ions and sulfate ions. The barium sulfate is going to stay together, and the copper 2 nitrate is going to dissociate into ions. So let's show that. I'm going to make barium ions and 2 nitrate ions. I'm going to make a copper ion, sulfate ion. Barium sulfate stays together, and on the product side I have copper ions and again 2 nitrate ions. So we have to pay attention to the subscripts, write them as coefficients, make sure everything's balanced in terms of charge and mass. At this point, we can start thinking about spectator ions. The whole point of a net ionic equation is it only shows the ions that are actually reacting. And that means the ions that aren't changing in any meaningful way, they have to disappear. So we need to cross them out. I see 2 nitrates on the reactant side. I have 2 nitrates on the product side. Those are spectators. I can cross them out. The copper ions also aren't changing in any way. They're copper ions on the left, they're copper ions on the right. They also drop out. I can actually just leave it in this form, and that's perfectly acceptable. The net ionic equation really just shows the formation of the precipitate. So barium ions react with sulfate ions in a 1-to-1 ratio to make the barium sulfate. And this is what you need to have for part A. Make sure that your net ionic equation is balanced for charge and mass. It should be showing the ions that form the precipitate, and make sure that those ions have charges or you're not going to get credit for it. The states of matter are not required. You might find them to be helpful, and you're certainly welcome to put them in there, but that's not going to affect your scoring. And all of this is what you needed to do to earn 1 point. Part B goes on to ask, calculate the number of moles of precipitate formed. Well, it's helpful that we've already written the net ionic equation because we know that the precipitate is barium sulfate. So if we go back and look at our data table, which I have here, I knew the mass of the dry filter paper. I knew the mass of the filter paper with the precipitate. The difference of these two values must be the mass of the precipitate. And so I can find the grams of precipitate, 1.136 minus 0.764, and I'm going to report that as 0.372 grams. Note the sig figs. I've got my mass of the dry filter paper and the mass of the filter paper with the product reported to the thousandths place. And when I do the subtraction, it needs to be reported to the thousandths place. Make sure you pay attention to those little details. And now we can actually do our grams to mole conversion. All right, I know moles is the number of grams divided by molar mass. And the molar mass of barium sulfate, I can look at my periodic table, add them all up, I get 233.39 grams per mole. So I have the grams, I have the molar mass. I'm just going to do that division, and I get an answer of 1.59 times 10 to the minus third moles of barium sulfate that were formed. This part of the problem was worth 2 points. It was 1 point for correctly calculating the mass of the precipitate formed. And the other point was for correctly using that information and the molar mass to find the moles of barium sulfate. The next part of the problem states, calculate the molarity of the original copper 2 sulfate solution. Here's what we know. We know that the net ionic equation is barium ions reacting with sulfate ions to form barium sulfate. They react in a 1-to-1 ratio. And the sulfate ions, of course, came from the copper 2 sulfate. I know how many moles of barium sulfate formed, and for my mole-to-mole ratios, however many moles of barium sulfate formed, I must have that many moles of copper 2 sulfate that reacted, because they're all in a 1-to-1 ratio from that net ionic equation. Therefore, I can state, without doing any additional calculations, 1.59 times 10 to the minus third moles of copper 2 sulfate must have reacted. We can use this information to calculate the molarity. We know that the molarity formula is moles of solute over the total volume of the solution in liters. This is on your formula sheet. You can look it up. We just found the moles of solute, and if we go back and look at the original problem, we know that we use 50.0 milliliters of that copper 2 sulfate solution. But be careful, that is in milliliters, and the molarity formula requires us to have our volume in liters. So we need to make sure we remember to do that, or we're not going to get a correct answer. My volume in liters is 0.0500 liters. So now I know the moles, I know the volume, I can substitute those in and calculate the molarity of the solution. And I got 0.0318 molar copper 2 sulfate, which is correct. And that's worth 1 point to put all that together. The problem, of course, goes on. These are the log free response questions. There's a lot of parts. For the spectrophotometry experiment, the student first makes a standard curve. The student uses a 0.1 molar solution of the copper 2 sulfate, and that was known to 4 sig figs, to make 3 more solutions of known concentration, 0.05 molar, 0.03 molar, and 0.01 molar, in 50 milliliter volumetric flasks. Part D says, calculate the volume of the 0.1000 molar copper 2 sulfate that you need to make 50.0 milliliters of a 0.0500 molar copper 2 sulfate solution. It's a dilution problem. And the easiest way to do dilution problems is this very handy equation, M1V1 equals M2V2. I had a certain number of moles of my original solution before and after the dilution, and so that's why this equation works. This is an extremely useful equation, and I do want to point out that you can use any volume unit with this equation as long as it's the same on both sides. In fact, you can use different concentration units. You're not limited to just molarity, although that's our most common one, as long as it's the same on both sides. So the way the problem is set up, I'm looking at this equation going, okay, I'm solving for V1. I want to know the volume of the original solution. In other words, the 0.100 molar copper 2 sulfate, that's M1. I know V2 is 50.00 milliliters, and M2 is 0.050 molar copper 2 sulfate. So I'm really solving for V1. And so I can take my equation and rearrange it to isolate V1. I know M2, I know V2, I know M1. I can substitute those values in, and I can get an answer, and I get 25.0 milliliters. And I know this to 3 sig figs. And if you do all this correctly, that's worth 1 point. Part E. Briefly describe the procedure the student should follow to make 50.00 milliliters of a 0.0500 molar copper 2 sulfate solution using the 0.100 molar copper 2 sulfate solution, a 50.00 milliliter volumetric flask, and other standard laboratory equipment. Assume that all safety precautions will be taken. We don't have to discuss lab safety in our answer, but we can use standard laboratory equipment. Basically, welcome to the world of volumetric glassware, folks. How are we going to do this? Well, there are really two parts to what we have to do. First, we have to measure out the right amount of copper 2 sulfate and do it precisely, and then we need to get it to the final volume. Really, that's where we need to start. How can we precisely measure out 25.0 milliliters of this 0.1000 molar copper 2 sulfate solution? And your best choice is to use a 25 milliliter volumetric pipette. Now, I hope that you've seen them, although I know my students this year didn't get to use the volumetric pipettes. Volumetric pipettes are a piece of glassware used a lot to measure a certain volume very, very precisely. They're one-trick ponies. They can only do one measurement. This is a 25 mil volumetric pipette. You can see it kind of has a shape like a rolling pin, really long and thin, and then this bulb in the middle. And then it's got one line on that upper arm. And that line is used to measure the liquid volume. For this particular one, if you look really closely at the picture, it's 25.00 milliliters plus or minus 0.03 milliliters. So a very, very precise measurement. All right. We know this volume measurement to 1/100th of a milliliter. And so what we're going to do is use a bulb to fill the pipette. And we want to bring the bottom of the meniscus of the solution to sit right on that line. And then we know that we have this very precise measurement. Other acceptable measuring options, you could say that you used a graduated cylinder. It would need to be a graduated cylinder marked to at least 1 milliliter. Or you could also use a burette to measure the volume. But the volumetric pipette is actually the best choice here, although those are acceptable. Your answer to Part E needs to be consistent with your answer from Part D in terms of the volume that you're using. But also, the idea that you knew what glassware you could use to precisely measure that volume, that's one point. The other thing I want to mention here is that you do want to keep your answer really brief. I'm not writing this in a test situation. I would not have written nearly as much if I were actually taking this exam in a timed setting. But that precise measurement of 25.0 milliliters, or even more precisely using a volumetric pipette, that's really all you need to say here. Part E mentions a specific piece of glassware, a volumetric flask. And again, I hope you're familiar with them, but you might not have gotten to work with them during class. Here's a picture of a volumetric flask. This particular volumetric flask, if you look at it closely, it again has one line. It can measure 50.00 milliliters really, really precisely, plus or minus 0.06 milliliters. It's the only volume measurement it can do. 50 mils, that's it. That's the only one you can count on when you're working with this volumetric flask. But it does it really precisely, which is exactly what we want here. What we need to do is transfer that volume that we measured with a 25 mil volumetric pipette and transfer it into our volumetric flask. And then add enough distilled water to bring the volume up to the 50.0 mil mark. So we need that meniscus to be sitting right on that line. Really good technique is you'd fill it partially, invert several times to mix it well, and then finish filling it up. I once wrote a 3-page essay on how to make a solution of known molarity. You can go into great detail, but again, you want to keep your answers short. Right? So if you talked about bringing it up to the 50 mil mark with your volumetric flask by adding water, that's the other point for Part E. So the student took the 4 solutions of known molarity and made a standard curve, plotting absorbance versus concentration, and we get this nice straight line. The absorbance of the copper 2 sulfate solution of unknown concentration is 0.219. Determine the molarity of the solution. I hope that you got to do a Beer's Law lab this year in class. It's always one of my favorites. In fact, I have a whole webcast on Beer's Law. We have this nice linear relationship. As the concentration increases, the absorbance increases. And all we have to do is read the graph to answer the question. My absorbance is 0.219. I read over and down, and I can estimate the molarity from that. I'm reading this to be about 0.036 molar. I do know on the AP exam last year that answers between 0.032 and 0.038 were accepted. You could have chosen to use this data to calculate the slope of the line and use the slope of the line and the y-intercept to calculate the concentration of the unknown, but don't make extra work for yourself. You can read it right off the graph. And that's what you needed to do for 1 point. The second student performs the same experiment. There are a few drops of water in the cuvette before the second student adds the unknown copper 2 sulfate solution to it. Will this result in a concentration for the unknown that is greater than, less than, or equal to the concentration that we found in part F? Justify your answer. I make the claim that the concentration of the unknown would be less than the concentration that I found in part F. Why do I think that? There are extra water droplets in the cuvette. That means the volume of the sample is actually going to be increased a little bit because of these leftover water droplets. And that means the concentration of the sample in the cuvette is actually going to be dropped compared to what it was in the original container that I made it in. And if it's got a lower concentration, it's going to have a lower absorbance. And if it's got a lower absorbance, I'm going to interpret the graph to give me a lower experimental value for the unknown concentration in part G than I had in part F. This part of the question was worth 2 points. 1 for your claim that the concentration of the unknown is less than, and 1 for backing it up appropriately. The College Board has a real emphasis on experimental error. Here's something that happened. Would it make your answer bigger, smaller, or the same? And why? This is a classic example of that. Another word to the wise. With these kinds of questions, lead with your answer. It's greater than, less than, equal to, whatever you think it is, and then why you think that is. So lead with the answer and then state your justification. So how'd you do? The average score on this question in 2021 was 4.44 points out of a total of 10, which is a fairly high average for an AP Chemistry free response question. If you earned 5 points, you're doing just fine. If you earned 6 or higher, kudos to you. If you got all 10, which was a very doable thing, you should be really pleased. This was a question that really looked at applications of some core lab skills in terms of precipitation reactions, gravimetric analysis, doing a Beer's law plot. So some good lab skills and some analysis in here. So all around a good question. If you found this helpful, like the video and leave a comment. And subscribe to my channel so you get all my latest updates. Practice chemistry every day. That's how you get better.